Hello everyone, I'm Fabio Busacca from the University of Palermo in the CNIT Research Unit of Catania, and I'm going to present the multi-layer offloading at the edge for Vehicular networks paper developed together with Carla Cirino, Cristian Grasso, Sergio Palazzo and Giovanni Schembra, all from the University of Catania. So, we will first see what is the reference system for our work and the model we developed. Then we'll understand what the optimal policy is in our work and how we can derive it. What are the simulation parameters for this reference scenario and the results? And in the end, we'll draw some conclusions and offer some hints for future works that could be developed starting from this paper. So, our work revolves around vehicular networks where vehicles are complex systems provided with connectivity, storage, and processing resources that let them communicate with each other and even with the existing mobile system infrastructure. So this enables the realization of a great variety of applications, starting from autonomous driving, but at the same time, whenever those applications require for very low latencies or massive computational resources, what happens is that local onboard devices may not be sufficiently powerful to cope with those demands. So instead, an external help is needed and may be provided by multi-access edge computing servers, which bring processing and storage closer to the user at the edge of the network, making even low latency application possible to be realized. Moreover, they make also job offloading at the edge possible. That is the paradigm where vehicles generate jobs, but instead of computing those jobs themselves, can ask Mac servers to do the work on their place. However, choosing how many jobs to offload and when to do it is a very complex task and calls for a proper studying of the system through robust theoretical frameworks. That is the main motivation for our work, which first proposes a novel multi-layer offloading scheme for vehicular networks, but most importantly, proposes a novel theoretical framework based on Markov chains to study the interactions between the actors in the system, that is, vehicles and Mac servers, and at the same time tries to find the optimal policy by also resorting to reinforcement learning techniques. So this is the reference system for our work. We have 3 layers, each one managed by a different stakeholder: the application service provider, the run Mac server service provider, and the backhaul infrastructure provider. At the vehicular domain, we have vehicles flowing on a road and generating jobs. This is the structure for a single vehicle. We have a job generator which passes jobs to an offloader decider, which can decide either to offload jobs or to keep them in the local queue. But in the latter case, the more jobs we keep, the bigger will be the delay. So instead, we have an entity, the Vehicular Platform Server, the VPS, which is in charge of choosing the optimal parameter queue, that is, the percentage of jobs to be offloaded to the Mac domain, so that Q% of jobs generated will be kept in, will be offloaded, while the remaining 1 minus Q% will be kept in the local queue. So, what about the Mac domain? There we have several Mac servers installed along the road. So while these servers could be up to n, in our work we do choose to keep only 2 of them to better highlighting and analyzing the evolution of the system performance as the simulation evolves and also as the parameters change. So in the Mac domain, just like in the vehicular domain, Mac servers can offload jobs to other Mac servers. But how can they do it? Well, thanks to the backhaul network domain, which is in charge of transferring jobs and results from one Mac server to the other one. Moreover, we have the Mac platform server, the MPS entity, which is in charge of tuning the parameters B1, 2, and sigma to improve the Mac domain performance. What are these parameters? Well, we'll discover this later. Moreover, our system focuses on a specific network slice handling vehicles moving in the same direction, for example, from the left to the right. So you can understand how backwards offloading does not make much sense, as once the computation is over, vehicles may be too far away to be easily reached by the results. So instead, we do only suppose to offload jobs from Mach 1 to Mach 2 and not vice versa. What is the system model? We have to understand how to evaluate from a numerical point of view the performance of our system. Starting from the vehicular domain, how can we build the reward function for the VPS? First, vehicles need to offload jobs, but this comes at a cost. So the first factor is the offloading cost mu. Then, whenever we offload jobs or process jobs, we spend some time. So the second factor is the mean job delay phi-v, which is computed by averaging the local delay and the remote delay. So the reward function in the end will be built like this. And as you can see, factors are normalized in 0, 1, and we also have two weighting factors, gamma 1 and 2, which help us choose what we want to value most in the expression, so that whenever we want a low delay, for example, but we do not care about cost, we can choose gamma 2 to be much bigger than gamma 1. What about the Mach domain? Well, in principle, each Mach domain server has at its own disposal several computing elements to process jobs. The more computing elements active, the faster will be processing, the more energy will be depleted. So the first two factors are power consumption, Xi, and job processing delay. Moreover, whenever we want to offload jobs to other Mach servers, we have to pay a fee to the backhaul provider. But at the same time, whenever we process jobs offloaded by the users, we get paid. So the third factor is the offloading utility theta, which is the balance between what we spend to offload jobs and what we get for performing offloaded jobs by the vehicular domain. So, in the end, the reward function is built like this. Once again, factors are probably normalized and probably weighed by factors C1, 2, and 3. How can we optimize the Mach domain? In principle, we can choose how many computing elements to turn on each server. So the first two parameters are the number of active computer elements, B1 and 2, on each server. Then we may also choose how many jobs to offload. So the third factor is sigma, the number of jobs offloaded. These parameters are chosen by the MPS by resorting to model-based reinforcement learning techniques. Now we have an overall system view. As I already said, at the vehicular domain, we want to minimize the offloading cost and the mean job delay by probably choosing the parameter Q. The bigger is Q, however, the more jobs we offload, so the more we will pay for offloading, but at the same time we'll minimize the delay. Vice versa, whenever Q is close to 0, we offload very few jobs, so the offloading cost is minimized, but instead the mean job delay is maximized. On the Mach domain, instead, we want to minimize energy consumption and Mach job delay, and to maximize the utility by tuning B1, B2, and sigma. So once again, we have a trade-off. The bigger are B1 and B2, the more will be energy consumption, but at the same time, the lesser will be Mach job delays and offloading utility. Or the bigger is sigma, the more we will pay for offloading, but at the same time, the lesser will be energy consumption and delay. In the end, moreover, Q is able to influence also the Mach domain. But why? Because the bigger is Q, the more will be the traffic offloaded to the Mach domain. And as the traffic changes, the Mach domain has to change its behavior too. So you can understand how maximizing both the reward functions is not an easy matter and calls for a proper studying through a robust theoretical framework, which is the main motivation for our work. So, how can we derive the optimal policy? We'll start with the vehicular domain. Here, as you may remember, we have to find the optimal Q percentage of jobs to be offloaded. How can we do it? Well, for each possible Q, we have to calculate the local delay phi L, but this is done in a very simple way, since local Qs are BB1K systems, and thanks to queuing theory, we can easily derive the delay phi L. Then, we have to receive the offloaded jobs delay phi m by the MPS, calculate the average, calculate the reward functions, and now we can choose Q equal to Q star in order to maximize the reward function. And in the end, we just have to broadcast the value Q to the vehicles. Doing optimal policy derivation for the Mach domain is instead a little bit more tricky, as we have to go across two stages. So the first one is understanding how traffic changes over time and therefore how job mission changes over time. While the second step is to model the job queuing in the system. But before we go on with explaining how we do this, we have to understand what a switched batch Bernoulli process is through a simple example about traffic lights mounted on a street. A traffic light can go across three states, red, yellow, and green. So we can accordingly build a transition matrix which describes the probability of going from one state to the other one. Then, basing on the state we're in, we expect more or less vehicles to leave the area. So whenever the semaphore is red, we expect no vehicles to leave the area. When it is yellow, we expect some vehicle to try to leave the street. But whenever it is green, we do expect all vehicles to leave the area. So we can accordingly build an emission matrix B whose single element is read like this. B3N is the probability of having n vehicles leaving the area whenever we are in state 3. So we do expect this probability to be high. So we just defined an SBPD process, which is completely described by its two matrices, transition matrix and emission matrix. Now we can speak about the job arrival process. So we have first to model how vehicles enter area 1, thanks to the arrival process omega. Then we have to describe how vehicles go from area 1 to 2, thanks to the transition process mu1. Then how many vehicles and how vehicles leave area 2, thanks to the departure process mu2. And in the end, also how many vehicles are in area 1 and in area 2, thanks to the Markov chains SN1 and SN2. These 5 elements define the Markov chain for job emission process, which will let us derive the transition and emission matrices for the SBPD job process lambda n. Now we just have to model queuing in the MEC domain, but this is done in a very simple way, since MEC queues have up to L computing elements and K available slots, so they can be modeled as Markov chains comprised between 0 and K. So S sigma is the overall Markov chain for the MEC domain system and appears like this. Now we can find the optimal policy. But how can we do it? Well, first we have to understand what an optimal policy is. In principle, it is a function that maps each state of our Markov chain into a specific action, that is the choosing of the parameters B1, B2, and sigma. But before we find the optimal one, we first need to understand what are the transition probability metrics and immediate reward metrics. The first one describes the probability of going from a specific state to another one whenever we perform action A. Whenever we do this, moreover, we will get some mean reward, which is indeed described by the immediate reward matrix. So thanks to these two matrices, we know for each state what is the best action and what is the transition produced, so that we know how the system will evolve over time. But knowing what is the best immediate reward does not translate into improving the overall average performance of the system over time. Because, well, you can think, for example, of spending your whole bank account in one day to get the best immediate reward, that is the best day of your life. But at the same time, the forthcoming days, you'll be poor and on the street. So we have to take into account future consequences for our actions. Reinforcement learning can help us. Whenever we build our system, we can resort to the Bellman equation, which is the expression for the cumulative reward, where future rewards are weighted by the so-called discount factor. Whenever the discount factor is closer to 0, we do only value the immediate reward, but whenever it is instead closer to 1, we do value future rewards a lot, and this is crucial for our system to work properly. So we found the optimal policy rho, and we can therefore calculate the mean job delay phi-m to pass to the VPS. Now, let's talk about the simulation. Here we have some parameters, but I can't go into details because of lack of time. So we will first see the plot for the overall delay suffered by jobs generated by the vehicles, as Q increases and as MPS weighting parameters vary. As you can see, whenever we do value delay a lot, we have accordingly that the red curve shows the lowest delay. Instead, whenever all factors have the same importance, the delay is maximized. We have also a middle case, the blue curve, where we do value a little bit more the offloading utility. So why is delay lower? Well, the reason is simple. If we want to maximize the utility, the offloading utility, we have to offload a little bit less. So accordingly, we have to activate more computing elements, and therefore we reduce the latencies. Here instead, we have the mean number of active computing elements in the MAC domain. As you can see, whenever we request for low delays, we have to activate a lot of computing elements, therefore consuming energy. Instead, whenever we do value each factor the same way, we have that the energy consumption is instead minimized. As usual, the blue case is in the middle. Here instead, we have the reward functions used by the VPS to choose the optimal Q star value. Let's focus on the blue circled curve, for example. As you can see, it is maximized for Q equal to 0.6. Therefore, Q star is 0.6 indeed. So as you can see, we have several curves for several weighting parameters for both the MPS and the VPS. So in this paper, in the end, we have described a novel multi-layer offloading framework for vehicular smart networks, studied the scenario through Markov Chain modeling, and provided an optimization method through model-based reinforcement learning, carried out a simulation with different weighting parameters, and highlighted how the whole system performance accordingly changes, and addressed some issues for future works, such as implementing a simulator to evaluate the accuracy of the model, or extending the model to include vehicle distance from radio access points. So well, thank you for listening.